So welcome to this talk. We are going to talk about the new Elasticsearch Java client that was released a couple of months ago. My name is Sylvain Wallez. I'm a principal software engineer. I work in the clients team at Elastic. The clients team at Elastic is responsible for all the clients library that you use in your applications to call the Elasticsearch server. So typically we have Java, we have JavaScript, Go, PHP, Python, Ruby, and so on as client library that we provide for you to integrate in your applications. So first, let's start with a new Java client. Why do we need a new client when we had one for a number of years already? So the current Java client is named the high-level REST client. It has a number of issues that the new client aims to solve. The first one is that it shares a lot of code with the Elasticsearch server. That was meant to ease the development in that server by using a common code base, but it turns out that it had some bad side effects. So namely, it pulls a large number of dependencies because of its relation to the server code. So typically, it will pull more than 30 megabytes of bytecode into your applications, most of which are not useful for a client application. It can sometimes be confusing because it shares a lot of code with the Elasticsearch server. Its API also exposes a lot of things that are internal to the server and that you don't have to care about and should not have to care about in your applications. It's also handwritten, which means that the API is not exactly consistent all the time. And for Elastic, it's a lot of maintenance work. Elasticsearch has more than 400 endpoints, and you can imagine how much work it is to maintain all that. And finally, it has no JSON to object mapping integration, which means that you have to map the byte arrays directly with your application objects, which is obviously not convenient. So the new Java client was an opportunity to take a fresh start. And first of all, it uses code generation. So it's based on the formal specification of the Elasticsearch API. We'll come back to that at the end of this presentation. And it is the first of a new generation of Elasticsearch client that will be entirely code-generated. Java starts first, next will come C#, and then we will have Go, Python, JavaScript, Ruby, PHP, and so on. 99% of this new Java client is code-generated, which means that we can very easily update, provide new patterns, and keep the client in line with the evolution of the API. It's also an opportunity to provide a more modern approach to a Java client for Elasticsearch by using functional fluent builders. We'll come back to that to see exactly what it means. And also provide a hierarchical domain-specific language that is very close to the Elasticsearch JSON format that you are used to manipulate in Kibana, for example, and also see in the documentation. And finally, it also provides automatic mapping to and from JSON with your application level classes by integrating either Jackson or JSONB or a number of object mappers. And last but not least, we keep compatibility with Java 8 because we know that it's important in many enterprise contexts to keep that baseline. And cutting the dependency with Elasticsearch also allows Elasticsearch to evolve on its own, and it recently switched to using Java 17, which obviously will be a concern in many enterprise contexts. So getting started, what it looks like to get started with this new client. So it comes with battery included, a number of components, but that means that some assembly is required. So to create an API client, we will first start by create the REST client, the one that you already know from the high-level Java client. That part deals with HTTP requests and responses and cluster node discovery. So it's a very low level that only deals with HTTP and byte arrays. You will have to create the mapper from JSON to your object classes. So we provide out of the box Jackson mapper and JSONB, which is the Java Enterprise mapper API. We then have to group those two into what we call a transport. The transport basically deals with everything related to encoding and protocol so that you can next create an API client. That API client only deals with Elasticsearch APIs and data objects that represent the requests and responses that are used for those APIs. These clients exist in two shapes: a blocking shape, the Elasticsearch client, and an asynchronous shape, which is the Elasticsearch async client. So whatever your programming flavor is, you're covered here. So let's see some practical examples. Here we will use an example with a product index. So a product, in our very simplified case, has three properties: an identifier, a name, and a price. So on the left side of the screen, you can see what you would typically use in Kibana when you're experimenting with the developer console. So we are putting a document in the product index, and the JSON contains the properties of our product. On the Java side, we can see here that, of course, we create our product, and then we will create an index request. So here we have the classical, I would say, builder style approach. We create a builder, and then we have a number of setters to set the properties of our index request. And finally, we build our request. Why we are using the builder pattern is that everything is immutable in the Java client, and the builder also allows to provide a chained setters that make it easy to construct complex objects. Once we have built our request, you see that we just call the client API endpoint called index with a request, and we're done. So the more modern approach is what we call a functional builder style. Instead of creating your builder object, the client.index endpoint will accept a lambda expression, and the single parameter of that lambda expression is the builder object that you will build on the fly, and then the client will just use that to send the request. So the benefit of this approach is that you don't have to remember class names. You say, okay, I'm calling the client, the index API endpoint, and then the IDE will guide you through auto-completion through all the properties that are available on that object. You don't even have to import any class. And of course, as you can see here, the last part of the request is the document that we're indexing, and we just passed the product. So this is where the Jackson object mapper will come into play by serializing your product into JSON. Now, a bit more complex example. We were going to search in our product index. So on the left, we see that we are doing a term query on the name field. So typically, we want to search for every product that has bag in its name. So using the classic builder style approach, we will start by first creating a term query. So in the new client, we find again what you may be used to from the old client, which is the builders, plural objects that are helper that give you access to all the variants of queries, aggregation, and so on. So we create a term query builder, then set its field. And from there, we create a search request, configure it saying we want to query the index, product index, set the query, and then finally, we send our search request. So the important thing here when we get the results is that we specify in the search call that we want a product class. And automatically, the client will use the JSON mapper to get back to your application object classes. So in the response, we get the search hits, we get the first one, we get 0, and then the source is not a byte array as it used to be, but it's directly your product instance. Now, if we look at the same request written with the new functional builder style, this is where we can see emerging a DSL that closely maps the JSON that we're used to write in the Kibana developer console. So if you look at the two side by side, they are very similar. So we create a we call search. We have a builder for the search request on which we set the index, we set the query. On the query, we will select the term variant. So your IDE will list all the different kind of queries that you have directly after hitting dot. And then we can set the fields of the term query, which are the field that we want to query and the value, the term that we want to match against. So this approach gives us a very convenient and easy way to build complex queries where you can have arbitrary hierarchical depth in your expressions. And so typically, as I said, the query is a union of all query types. So we allow to have completion-driven discovery. There are something like more than 50 different query types in Elasticsearch, and I think more than 60 different aggregation types. You cannot memorize all of them. So the IDE is here to help, and you just hit dot and let the IDE tell you what comes next. Sometimes this DSL approach can become a bit complex when you have deeply nested queries. So you can still split it and have different subparts of your query as independent objects. So here we see another helper from the new client, which is the auth method. So you have the class name of the final object, here term query, and then you call auth. And the parameter of that method is a builder lambda expression. So here we prepare our term query, and then we assemble the search request by setting the index and inserting our query as the query property. We specify the product class to say how we want to map the results, and there we go, we can get our product back. If we go into aggregations, which are the other very complex part of Elasticsearch, it's a bit similar. So here we will run an aggregation on our product index, returning a histogram of products by price range, having the number of products in every range. So we call search again. We set the size to 0, saying we don't want any document back, but only aggregation results. We name our aggregation price histogram, and then again with the union auto-completion from the IDE, we choose the histogram variant and set its fields, price and interval. And we will say here that the target class that we set on this search query is void. What does it mean? Is since we set the size to 0, there will be no result document returned in the query, and we don't care about setting a class that needs to be mapped from JSON. So we just say, okay, this is void, and any document that will come back from the search request will just be ignored. So now, navigating the aggregation results is always a bit complex because of all the variety of aggregations that we have. So on the left, we see that aggregation comes back as a dictionary, where we have the name and the type of the aggregation, like histogram, hash, price, histo. And under that property, we have the aggregation buckets. So in Elasticsearch, buckets come in two forms, depending on how you configure your aggregation, either arrays or a map. So typically here in the Java code, we will follow the structure of the JSON by first getting our aggregation by its name, then casting it to its actual variant. So the interesting here is that you don't have to do a Java cast. The named aggregation is actually a disambiguation wrapper object that provides all the variants that you can expect from an aggregation result. We just select the histogram variant, and from there we can navigate to our buckets, get the array form of buckets, and finally get the first bucket and its document count. So the key point here is that the new Java client drives you completely through navigation of complex object hierarchies without requiring you to cast your objects or even know about the actual class names of those objects. It's all completion driven from the IDE. So let's have a look at what's behind the scenes. Where does this Java client come from? How have we produced it? So first, obviously, when you want to generate code for an HTTP API client, the first thing we are thinking about is to use OpenAPI. So it turns out that OpenAPI isn't a good match for Elasticsearch. The reason is that Elasticsearch API is complex and is not canonical. So this is an API that has grown more or less organically over the last 10 years. And there are a number of flavors depending on the endpoint you are considering, and also some things that simply cannot be expressed in a very usable way in OpenAPI. So capturing this API with OpenAPI would have required a lot of extensions. Along with that, Elasticsearch has more than 400 endpoints that go down to 2,000 structures, and well, honestly, describing this in YAML would have been a nightmare. So we took a different approach. The thinking is that there's a language that exists that can be represented, that can be used to represent types in JavaScript and JSON. That language is TypeScript. So the Elasticsearch specification that is used to generate the code is entirely written in TypeScript. The advantage of this approach is that we have very strong support from IDEs. We have an executable specification that can be used to run a lot of tests, and it is static type checked directly in development environment. So you can find this specification. It's open source and public at GitHub Elasticsearch specification. We don't expect people to contribute directly to this GitHub repository, but you can. I mean, if you find a discrepancy in the API or something that should be made more detailed, or some fields are missing in the API definition because it's so wide that we sometimes forget some fields, please go ahead there and contribute. That would be more than welcome. So typically what it looks like, so here's an example, which is the index request that we used previously to store documents in our product index. So the TypeScript structure that we can see here has a generic parameter. So it's named tDocument, and it represents your application objects. This generic parameter is what allows, when we generate code, to map this parameter with the JSON object mapper. It extends a request base that captures a number of common parameters, and then you can see that we have three parts. So the path parts, which are property that go into the URL path of the API, then query parameters, and then finally the body, which here is our tDocument. So this TypeScript definition is then parsed and compiled into an intermediate form that is fed into the code generators. And this is what allows us to provide a strongly typed, consistent API in the Java client. So the process looks a bit like this. We have our specification TypeScript files that go through a specification compiler that is also in the same GitHub repository, and that produces a giant JSON file that contains everything in a standardized form that captures everything that is specific to Elasticsearch. And from there, we have a number of code generators that create the final clients. So what's next for the Java client? The number one request that we get from users is documentation. Working on this new client was a huge amount of work, and we wanted it to be ready a few minor releases before switching to the new major Elasticsearch 8 release, because for the reasons I mentioned previously, the existing high-level Java client will be removed from version 8. So that was a tremendous engineering effort, and of course, documentation is lacking a bit. So this is the next big topic for us: improve documentation. Number two priority is also a number of helper objects. So you probably know the bulk processor from the high-level client. That one is still missing. We're going to add it. Something I haven't mentioned that is an important point to mention is that the new client and the old high-level Java client can work side by side in the same application and sharing the same low-level HTTP client, which means that you can have a progressive transition from one to the other with no operational overhead because they will share the same network connections. Next on our roadmap also is additional components, typically as using the Java 11 built-in HTTP client. So since Java 8, the JDK includes a lightweight HTTP client that will allow for more lightweight deployments where you don't care about all the features of the Apache HTTP library, and also include, depending on the feature requests, other object mapping libraries. Typically, the next candidate will be JSON, which is the second most popular JSON library after Jackson. So that's it. Thank you for listening, and please get the new Java client and give it a look at elasticsearch.java. Thank you.